Hi everyone, UCI Physics. Let's talk about statistical physics. Everything around us, from the air we breathe to the stars in the night sky, is made up of tiny particles. These particles are constantly moving and interacting with each other. Statistical physics is the study of how these microscopic interactions give rise to the macroscopic properties of matter that we observe. Imagine trying to predict the movement of a single gas molecule in a balloon. Now, imagine trying to do the same for all the trillions upon trillions of molecules in that same balloon. It seems impossible. That's where statistical physics comes in. Instead of focusing on individual particles, statistical physics uses statistical methods to analyze the behavior of a large number of particles. By considering the average behavior of many particles, we can make predictions about macroscopic systems. This approach has been incredibly successful in explaining a wide range of phenomena, from the behavior of gases to the properties of solids. Think about a glass of water with ice cubes. Statistical physics allows us to understand how the water molecules in the liquid phase interact differently than those in the solid ice. It helps us explain why water expands when it freezes and why ice floats on water. These principles are not just confined to the laboratory, they are essential for understanding the world around us. One of the key concepts in statistical physics is temperature. We often think of temperature as a measure of how hot or cold something is. However, in the world of physics, temperature has a more fundamental meaning. It is a measure of the average kinetic energy of the particles in a system. In simpler terms, temperature tells us how fast, on average, the particles are moving. The higher the temperature, the faster the particles move. As particles move faster, they collide with each other more frequently and with greater energy. These collisions are responsible for transferring energy in the form of heat. Understanding temperature at a microscopic level helps us explain macroscopic phenomena like heat transfer, thermal expansion, and phase transitions, such as water boiling or freezing. Consider a pot of water on a stove. As the burner heats the pot, energy is transferred to the water molecules, causing them to move faster. This increase in kinetic energy corresponds to an increase in temperature, which we can measure with a thermometer. The faster-moving water molecules collide with each other more frequently and with greater energy, eventually leading to the water boiling and turning into steam. Another important concept in statistical physics is entropy. Entropy is often described as a measure of disorder or randomness. A system with high entropy is more disordered than a system with low entropy. For example, a shuffled deck of cards has higher entropy than a brand new deck where all the cards are in order. Entropy is intimately connected to the idea of probability. There are many ways to arrange the cards in a deck randomly, resulting in high entropy. There are far fewer ways to arrange them in a specific order, resulting in low entropy. Statistical physics shows us that systems tend to move towards states of higher entropy. It is more probable for a system to be in a disordered state than in an ordered state. Imagine dropping a single drop of ink into a glass of water. The ink molecules will spread throughout the water, eventually becoming evenly distributed. This process is driven by entropy. It is statistically more likely for the ink molecules to be spread out randomly than to remain concentrated in a single spot. The laws of thermodynamics govern how energy behaves in systems. They are fundamental principles that apply to everything in the universe. Statistical physics provides a powerful framework for understanding these laws at a microscopic level. The first law of thermodynamics states that energy cannot be created or destroyed, only transferred or converted from one form to another. This is also known as the law of conservation of energy. The second law of thermodynamics states that the total entropy of a closed system always increases over time. This means that the universe is constantly moving towards a state of greater disorder. The second law also tells us that heat naturally flows from hotter objects to colder objects, never the other way around. While these laws may seem abstract, they have profound implications for our understanding of the universe and our place in it. Think about the Earth receiving energy from the sun. This energy powers life on our planet, drives weather patterns, and influences the Earth's climate. The laws of thermodynamics dictate how this energy is transferred and transformed, shaping the world we live in. Understanding these principles is essential for addressing global challenges like climate change and developing sustainable energy sources. Thanks, everyone. Next, we talk about thermodynamics. Catch you in the next one. Stay with UCI course.